How's it going, everybody? So, like Chris said, we're going to be talking about desktop metal today. This is going to be just a quick overview of the Desktop Metal Studio system, which is the metal 3D printing system that is out now, and as well as going over a little bit of the production system that Desktop Metal is developing, and that's going to come pretty soon here. Let's get started. This is definitely more geared towards people that have no Desktop Metal experience, so I haven't really seen it yet. So for those of you that have seen it, Desktop Metal was founded in 2015 by a lot of different leaders in the additive manufacturing world, the metallurgy world, and just the 3D world in general. And they wanted to make metal 3D printing accessible for engineers and manufacturing. So not just large-scale metal 3D printing service bureaus, but actually just have it be able to be in-house for designers and people to really use. So the metal manufacturing market is obviously very large. $1 trillion in metal parts produced by the top 10 countries. Metal 3D printing is a very small chunk right now of that $1 trillion metal market. Only at about $1 billion. Because right now, metal 3D printing is only really just scratched the surface. It's just too expensive for prototyping, it's not fast enough, or it's not low cost enough for mass production. And that's kind of the state of metal right now. But with Desktop Metal, they're really trying to change that. So it's really all about the change. Because today's metal 3D printers are typically similar to how, if you were going to compare them to a 1970s punch card computer, where the systems were just really, really large, really expensive. The environmental requirements for the machines are pretty large. The materials are very limited. They're very labor intensive. You need expert operators. A lot of these metal manufacturing, laser sintering and things like that, need explosion-proof rooms and 480-volt three-phase with respirators. And it just becomes a very large process, and that's kind of the state of metal 3D printing for the most part right now. Desktop Metal is quite a bit different. It's really the first office-friendly metal 3D printing system. So this is the studio system. And so this is a three-piece, three-system setup where we have a printer, a debinder, and a furnace. And we'll kind of talk about what this whole process looks like and where each of those pieces of equipment come into play. But first, it really is safe for the office. That rod in that guy's hand, that is the printing stock. So we're not ever dealing with metal powder in the air, and that causes a lot of hazards. You don't need a respirator or any ventilation. It's very safe. You can handle it with your hands. We're not really worrying about any dangerous lasers or any third-party equipment. Supports aren't being welded to a metal sheet or anything like that. It really, truly is safe for the office. We have these systems already set up in offices around the country. Powder bed fusion sits at over $1 million. By the time you buy the printer and all the support equipment, and you make those facility changes and hire the expert operators for those machines, you're really always looking at least over $1 million in investment just to get one of those machines set up. Whereas the Desktop Metal Studio system, you're sitting under $200,000. And you don't need dedicated operators. It really is just like a normal plastic 3D printer where any engineer in your facility can utilize the equipment to its best advantage. So the technology for Desktop Metal comes about from the metal injection molding industry. If you're familiar with metal injection molding or not, it's a very mature technology. It's been around for a while. It's used for a very large variety of different parts, usually fairly small parts for metal injection molding. But the technology is pretty much the same that we're using. So how metal injection molding works is we mix a metal powder with a plastic polymer binder into a feedstock, and then that feedstock is then basically injection molded just like you would injection mold any other part. Now you have your injected molded part, which is this metal powder polymer blend. You put that into a solution and you debind it, which is removing the primary binder or the plastic or polymer out of the part. And then you place that part into a furnace to sinter. That raises the temperature of the part up to just below its melting temperature. And then it shrinks to fill in the voids left over by the binder. And then sinters to be a fully dense metal part. So that's metal injection molding. Desktop Metal follows pretty much the same process, but instead of injection molding, we're skipping the tooling process and the injecting process, and we're just directly printing our green part, right? So like our injected part, we're just printing it instead. So our feedstock, instead of being granites and pellets, is just these rods that are already made. They're mixed with metal powder in the binder, just like the feedstock before. And then we're skipping the molding process, and we're just directly printing our part. So we don't need any tooling. Once our part's printed, we put it into that same solution, that debinder solution, to pull out the primary binder, the polymer binder, and then we place our part into a furnace to sinter. Same system. So it's a three-piece system. We have the printer, we have the debinder. The debinder's on the left, printer's in the middle, and the furnace there on the right. So the printer is very similar to pretty much any traditional FDM sort of process. It's familiar design guidelines. It really is powerful of a printer as any other FDM would be. With a build size about 12 by 8 by 8, But you have to consider that because the parts are going to be shrinking during the sintering process, we do have to scale our part up about 20%. You don't have to figure out the math to do that. Our program does it automatically. But just keep in mind that the actual final build size is going to be no larger than about 10 inches by 6.5 by 6.5-ish. So you see we have resolution there, speed, footprint, all pretty similar specs that you would see for a plastic printer. The way the material works is they just come in these little cartridges. So the material is really easy to change. You're not dealing with filament on a spool or anything like that. And again, we're not handling any metal powders, which are pretty dangerous. So these heads are really easy to change. They just quick release. And if you're familiar again with traditional metal printing, changing materials out in that laser-based system is very, very timely, very costly, and poses a lot of safety risks and exposure to those metal powders. So this is quite a different setup just to quickly hot swap these material cartridges in and out. But you can see here, you can see the internal structure of this print. Again, just looks like a normal FDM printer. You know, we have a sparse infill. We can do some solid infills. We have a support raft. We have printing supports and things like that. Very similar. There's the printer right there. So it's a dual extrusion. So we have our model material, or our metal and powder blend. And then we also have a ceramic interface as well. So you kind of see it in this picture. This is a blade, but we have our supports growing from the raft at the very bottom. Then with that white line, sort of right underneath those blades, that white line is a ceramic interface layer that when sintered basically just turns to dust and allows our parts to not weld itself to the supports. So our parts can just come off by hand usually. We don't need the machine supports off like with most metal 3D printing. You have to use wire EDM and things like that. But in this case, we don't have to. But also this picture is also showing that green parts, so right after they're done printing, they're in this clay-like state. They're pretty soft. Solid enough to handle fairly well, but they're soft enough that you can sand it really easily. So it's a lot easier to sand a piece of clay than it would be a piece of metal. So this is a cool thing you can do with some of these, this green state. So once we're done printing, once we've done a little bit of sanding, we throw it in the debinder. And generally what we're doing is we're going to be batch loading the debinder. So you might have 5, 10, 15 parts in one debind cycle. And then it's just using a solution, and it's automatically distilling and recycling that solution as you're using it. And again, this is another piece of equipment that's safe for the office. So it's not going to be releasing fumes. So it's a dry process, meaning you're never touching any of the chemicals at all during the process. This is kind of what's going on the inside. So you can see you put your parts in dry, and then it fills the debinder with this solution. And then once it's sat in there for a predetermined amount of time, again, you don't have to figure it out. The system and the software figures out the amount of time that it needs to sit in there. The fluid will drain, dry, and then you pull your parts out. And then lastly, you throw your parts in the furnace. Obviously, you're never actually going to be seeing the parts red hot like this. But just like with the debinder, it's going to be a batch loading process. So you'll be throwing your parts in, and then you might have 5, 10, 20 parts stacked up on different ceramic trays, kind of like you would see in a normal furnace operation. You don't need to know metallurgy. You don't have to be an expert in that field. This software will automatically determine what temperature it needs to ramp up to, what the temperature profiles need to look like, how long it needs to cool off, and all that. It's really, there aren't really many furnaces like this. This is a pretty big deal. This is what's really changing about this setup. It's really the furnace. The printers, you know, that's an FDM printer. It's pretty typical. But the furnace, being an office-friendly sintering furnace, is pretty amazing. It fits through a door. You really don't need a lot of special facility requirements for this. And unlike laser-based systems and other some traditional metal 3D printing, because we are doing this heat treatment, there's not going to be any residual stresses that are normally introduced. And like I said, the metallurgy is built in. You can kind of see there's the temperature profiles there. You don't ever have to know what you're doing when it comes to sintering metal. You just put your parts in. All you're doing is you're bringing in your CAD to fabricate, which is the software Desktop Metal developed, and it automatically generates supports, generates tool paths, scales the part what you need to do, and then it manages your part along that process and knows where it's at, whether it's been sintered, whether it's been debinded, and knows how long it needs to be in each of those steps. And in the end, we're left with near net shape parts. So there's similar accuracy and resolution to FDM sort of printing. And in fact, I've seen parts that turned out and look a lot better than traditional plastic 3D printed parts as well. And so you might be asking, what was the end result for the metal? The densities are similar to metal injection molding, and they're similar in performance to, say, a casted part. So where we are still getting the benefit of using metal in this case. And since MIM, the metal injection molding, has been around for a while, there's a lot of alloys that are already been developed, and there's already a supply chain for these metal injection molding materials. And since it's the same material and the same process, It's only a matter of time before we can easily develop these materials for desktop metal. So right now we have 17.4 pH stainless steel, and we have 316L stainless steel are currently available for printing, with some more on the way. So here's an idea for those that haven't seen some traditional metal manufacturing. They're on the left, 3D metal printing. Those supports are welded to the part, and they're also welded to steel plates on the bottom. So those require quite a bit of machining and post-processing just to get the parts off of the tray. And then to get them nice and smooth and is even more work of sanding and polishing and all that. There on the right is our parts, and you can kind of see some of those supports have already been removed. You see some of the powder, that pinkish kind of powder on the ground. Those were the ceramic supports that just turned to dust. And then in the video, this guy just pulls this part off of that support and support raft with just a nice little tug. So pretty much completely, you can remove all the supports by hand and not needing extra machining and things like that. So I've talked about the software a little bit. So this is Fabricate software. It really is a very powerful software. All you do is you just import your STL or your IGES step file, or you can bring in your native CAD files like SolidWorks files. You bring them in, and then, like I said, it automatically scales it up to what it needs to do. And then it will generate supports and contours and all those sorts of things, just like on the normal 3D printing slicer would. It gives you a lot of options to rotate your part and a lot of ability to adjust some of the settings, like we're doing contour widths or number of contour lines, solid wall thicknesses, sparse fill densities, interface densities, tons of different things you can change and manipulate yourself just to get all the little tweaks you want out of there. But they also have really good default settings as well. And so once you have your part oriented and set up the way you want it, it'll track it through the 3 stages. So once you have the part set up for printing, it'll be in their queue and say it's ready for printing. Once it's completed printing, it'll automatically be put into the debind queue and say, hey, this part is ready to be debound. So then you can go and select, 5, 10, 20 parts in your debind queue. So you tell the debinder, hey, I'm loading all these parts, and it tells you, okay, here's where you need to put them. And then once you're done debinding, now those are automatically going to be thrown into the sintering queue. And then in the same way, you start the sintering job, it'll tell you, hey, here's all the parts that are ready and available to be sintered. And it'll tell you where to place them on what trays, and then automatically figure out all the metallurgy needed to sinter those parts completely. So it's a very powerful software. It's really cool. And that's it for the studio. Cool. So lastly, we're going to go do a quick overview of the production system. So this is a system that is not currently released to the public yet. We have some pioneer customers and beta customers, but this is more geared towards production, as the name would imply. So it's 100 times faster than other metal 3D printing and at 20 times lower cost. Okay, cool. That sounds like some cool buzzwords and looks really neat. But why is that? What does it really mean? Well, this system is, again, using the metal injection molding kind of idea, which is why it's so much cheaper. That all of those materials and processes are already in place. But this machine was created by the same inventors of the binder jetting and the single pass ink jetting technologies that have been around. So this single pass jetting builds parts very, very fast. We're not going to be dealing with sort of the extrusion process like with the studio system. This one is much more like a jetting system, and it has a much larger build tray as well. Basically, the way that these work is they have a big print head that comes by and jets the layers layer by layer, and it has a roller that comes by and rolls over a new layer. So what the single pass jetting is that every time the print head moves over the build tray, it's printing a layer. And so it has rollers and print heads on both sides of the printer. So as it goes back and forth, left and right, each pass is another layer. And that allows it just to print a lot faster than any sort of extrusion or laser process could. So with the laser processes right now, all the parts, like I've said, are usually welded to some sort of steel bed. And so you're limited to just doing pretty much one layer of parts, and all those parts are requiring EDM. You can see on the right, that is the entire 13-inch by 13-inch by 13-inch build chamber that the production system can print in, so parts can be nested. And that's because, like with other jetting processes, or powder jetting processes, the powder inside the chamber is supporting the parts. And so you can print from top to bottom, and the whole thing's going to be full of powder, all supported, and then you just have to dig your parts out afterwards. So that just allows a lot higher productivity per each build. So looking at laser powder bed fusions compared to DM productions, compared to casting, that top line is the traditional laser powder beds, and those are cost per part. So you see it's a nice straight line. Same with desktop metal production system. It's a good straight line, but the cost is a lot lower. All 3D printing is pretty much the same when it comes to this cost per part. No matter how many parts you do, generally the cost stays exactly the same. compared to casting, as you do more parts, right, it becomes a lot cheaper, and everyone pretty much understands that. But what's important to see here is that because the DM production cost per part is so much lower, that intersection point between when casting outperforms a desktop metal or 3D printing, that intersection happens a lot lower and a lot higher volume. And that means that basically, if you're still, in this case, 100,000 is kind of the estimate in this case, if you're doing 100,000 parts or less, it's still going to be cheaper than casting. Whereas with laser powder bed fusion, that volume might be 10 or 20 parts as a break-even point for the laser powder bed. So it's much more production-based. And like I said, shipping to Pioneer customers now in 2019. So if you're interested, please contact us. I believe sometime in 2020 is when they will start shipping. So we've looked at 2 different desktop metal systems, and really these cover the full product life cycle. So you have the desktop studio system, which is going to be just for prototyping, really. You're not going to be doing much end-use parts on the desktop metal studio system unless there may be one-offs or you have very, very low volume. And then the production system, which is obviously for mass production. The studio system is really the office-friendly one. That production system is not really an office-friendly environment. We are dealing with some powders and much larger systems as well. But they're both using the same metal injection molding technology. And that just brings the cost per part way down. The material costs are a lot less because we're using these similar parts that have been around for so while. That's really all I had. It's not a lot. It's a quick overview, but questions are definitely welcome.
Yes, Cody, we did get a couple of questions.
All right, cool.
The first question is, any insight for the schedule of some of the materials in development?
Yes, I know. So 316 was just released, and then I believe the 2 ones that are next up on the list is going to be, I believe they're focusing heavily on the Inconel material, which is a super alloy, and then copper as well. And I've seen some copper parts. They're pretty cool. So I know that those are in development. As far as a schedule of when they're going to come out, I'm not sure. I just know that those are next on the list. I would expect by the end of the year, if not maybe Q1 of 2020 for Inconel at least, or maybe copper, one of the 2.
Here's a couple other material questions asking if either aluminum, aluminum alloys or titanium is available for this.
Neither are currently available. I know they're both in the works. Those are 2 materials that are in the metal injection molding world. I believe titanium will probably come out before aluminum. Aluminum is a fairly tricky material when it comes to sintering, so I do think titanium will be out before aluminum, but I know that both are in the works, so you never know. But as far as scheduling and timing goes, Inconel and copper are likely to come out before titanium, and then that probably before aluminum as well.
Excellent, thank you. Let's see here. There was a question about cost for a typical system and trying to approximate the cost per part, if possible.
So for the studio system, I believe, and I'm not a sales guy, so don't quote me on some numbers here, but it's going to be just under about $200,000 when it comes, after maintenance costs and installations and things like that. You're looking at just around $200,000 for that. The cost per part is going to vary so wildly. I'm not going to try to give you an estimate. If you're curious about cost per parts, if you have a specific part you want to look at and see how much it would cost for the material, contact us and contact your local sales rep or local AE, and we can bring your part into our fabricate system and kind of give you a nice little tour, fabricate, and then also just give you a good estimate. There's a good estimating tool in the software that can do that for us.
Excellent. All right. What about question, thermal profiles for the furnace means that only that first furnace is necessary? I don't quite understand the question, sorry.
Basically saying, are all the future material options going to be available on just that one furnace, I think is the question. And yes, I believe that is the idea, is that the one furnace should be able to do all future material profiles. Hopefully that was the right question.
You nailed it. Just got confirmation on it. Thanks, Cody.
Cool.
Considerably more eloquent on the metal 3D printing than I am, that's for sure. See, last question here. For the prototyping system, do captive support structures need to be avoided?
Do they need to be avoided? Well, they need to be avoided if you don't want them. The question is, basically, if there's an internal structure or an internal pocket for supports printed that you can't get to it, right? So there's no way to remove it. I believe if you're okay with the support being there, and if it's not an issue with the support being there, that's fine. But there are definitely instances right now where those captured supports are just really hard to remove or can't be removed. Now, something they're working on in Fabricate is to have it automatically slice up supports. It'll basically recognize that there's captured supports, and it'll try to break the supports up into small pieces so that you can fit them through whatever hole or entry there is. But you are right. That is kind of a difficulty with these sort of removal supports to be removed. But I've had customers that they really are just concerned about the outside structure, not so much about the internal structure sometimes. So kind of just depends part to part. You can also another answer to that question could be that you can also could potentially design in your own supports to be removed. If it's if you're designing like say if you had a pocket. And what you could do is design the roof of that pocket to have self-supporting angles, like a 45-degree angle. So instead of the pocket coming, maybe rounding off or becoming flat, that pocket now has like a 45-degree roof. Then now supports won't be printed inside there. So there are some opportunities to fix those problems.
Excellent. Thank you, Cody. That was the final question that I saw from the chat.
Great. All right. Well, thank you, everybody. That is all I had. And here's some of the upcoming webinars as well.
Perfect. Thank you, everyone, for joining us. Thanks, Cody, for going over that. And you can see here we've got listed our webinars for June. Hope to see some familiar faces in that list. And with that, I will say thank you to everyone and have a great rest of your day.